In this tutorial, we'll start doing image processing with real images and make a big step towards automating Where's Wally. We will be learning about and implementing different operations from classical image processing to do things like blur images and detect edges. Once we can do this, we're only a few steps away from finding Wally. Most of the inspiration for this tutorial series came from Peter Corke's Robotics Vision and Control book. So if you finish this tutorial series and really like image processing and computer vision and want to learn more, definitely check out this book. An important operation in image processing is a spatial operation. Spatial operations are generally defined over a window. So we take our input image I and look at all the pixels within that window W, and that will tell us the value of the corresponding pixel in the output image. One important spatial operation is a convolution. A convolution is a spatial operation that uses a matrix referred to as a kernel that is the same size as the window and simply multiplies the elements together and adds them up. This is how we'll blur images and do edge detection and similar operations like that. But as always, we have to be careful. Spatial operations are not defined on image boundaries because the window hangs over the edge of the image. There are typically two ways around this. We can introduce rows and columns of zeros around the image, or we can just not calculate the operation for the edges. But either way, we need to be careful. Here we have a window with width and height 3, so we can't do a spatial operation on the edges and corners of this image, because the output is not defined. But if we pad the image with zeros around the edges, we can now perform a convolution or other spatial operation. But now, the input image is not the same size as the output image, so we need to be very careful with indexing. So in this tutorial, we'll be importing data, manipulating the data to get around boundary effects. We'll be writing a function that takes in an input image and a kernel, and then convolves the two and outputs the result. And as always, we'll be producing quality plots. So let's move over to Matlab and get started. In this tutorial, we're going to be writing this function called image_filter, which takes in an image f and a kernel t, which is just another matrix, and performs a convolution between the two and returns the output. In this tutorial, we won't be looking at any of the material we've already covered, so we won't be looking at setting up plotting or reading in data or doing any plotting operations because we've covered all that before. Here we're going to focus on writing this function called image_filter, which performs a convolution. And I've left all the hints in here from the template just so that we don't get lost as we're recording the video. So the first thing to do is f, since it's going to be an image, it's going to be integer data, not floating point data. So, but now we don't want it to be integers anymore. We don't need it to be a valid image, so to speak. We want to do mathematical operations on it. So let's just override it with a different version of itself. So we'll just use the function double to convert f from whatever it was into a double. And now that we've done that, we'll just delete that hint. We've also initialized the output here to be the same size as the input. Now, it's going to be important that we know the size of everything we're working with, since we're going to be indexing through f. And we need to know the size of the kernel as well. So let's use the function size to read in the size of the matrix f. And we're going to store that in two variables. We're going to use, let's say, fv for the height and fu for the width. So stored in fv and fu will be the height and the width of f. We'll do a similar thing for the kernel t. We'll store that in tu and tv. Okay, and the next thing we should do is figure out how much we need to pad our input image by so that our convolution's defined all the way to the edge of the image. Now, an easy way to think about this is if you were to center the window or the kernel in the top left pixel of the image, how many pixels would be hanging over the edge of the image on the top and how many pixels would be hanging over the image on the left. And that's always going to be the width of the kernel minus 1 and then divided by 2. So that'll be, let's call that dv. Let's call this du. So this will always be true if you're always centering your kernel around the center pixel. And delete this hint now that we've done it. Now we want to take our input image, F, and we want to pad it with zeros all around the border. And Matlab's got a function for this called pad array. So we'll go fp equals pad array. Now we've never used this function before, so we should look at the help documentation. So it looks like we just give it the matrix, the size of the padding, the value that we want it to pad it with. In this case, we'll use zeros. And then we want to tell it whether we want it to put the zeros before the image or before the matrix or after the matrix or on both sides. So we can call pad array with F, the input, and then the size, which is going to be dv du, and then we want to pad it with zeros, and we want to pad it on both sides. Now if we put a breakpoint here and we hit save, we should be able to run tutorial 5. Now the function doesn't do anything useful yet, but this is the input image. Now F is 384 by 512 and our kernel is 5 by 5, so we should get an extra we should be adding 4 to both sides of F. So 384 by 512, 388 by 516. So we added 4 to both sides, so that's doing the right thing. And if we open up F, and then we open up FP, we've got FP is just F padded with zeros. Another useful variable to create is the relative rows and columns that we want to index. So let's say that we've got this submatrix. Let's just exit debugging. So we've got a matrix A equals rand 5 by 5. Let's say we want to grab the center 3 rows and columns. So we want to grab a little square matrix made of these elements. We can go A 2 to 4, 2 to 4, and now that should grab for us this center matrix here, which has these 9 elements in it. Another way to do this would be if we were indexing over the matrix A and we had a little window that was 3 by 3 that was centered about the center pixel. So the center pixel here is A33. But if we're centered around that pixel and we want to step to the left of it and step to the right of it, we can also do this. We can go A plus minus 1 to 1 plus minus 1 to 1. And now what this should do is this should do the exact same thing as A 2 to 4. Because minus 1 to 1 gives us this result, and then minus 1 to 1 plus 3, that's wrong, minus 1 to 1 plus 3 gives us that result. Let's call this variable v, and that's going to equal negative dv up to dv. So if we've got a 5 by 5 kernel, this should be -2 all the way up to 2. So -2, -1, 0, 1, and 2. The same thing with U. Okay, and now we're going to do the convolution. So we need 2 for loops. We need one to control looping over the rows and one to control looping over the columns. So we'll use for I equals 1 up to, in this case, FV. And then for J equals 1 up to FU. So I loops over the rows and J loops over the columns. Now we need 2 things. We need to define the patch. So this is the submatrix centered around the pixel, the pixel we're after, the pixel we're looking at. And then we will perform convolution and set Gij. So to define the patch, we just need to use these little temporary variables we defined here. So our patch is going to come from our padded matrix. And here's where we need to be careful. We're going to be at pixel I plus dv, because that's the width of the border of the width of the padding. And then again, now we're going to add our relative indices v. I'll do the same thing for columns, j plus du plus u. So that defines our patch. So when I is 1 and j is 1, we get, okay, so we should be able to, if we open up this again, our first patch should be these 5 elements here. So if we just open up our patch, good. And then if we move along, step again, we should have just moved along one. So now our matrix should be these 5 elements, which it is. Good. So the next thing to do is, now that we've defined our patch, is to multiply the patch and the kernel together. And we'll just do that using dot multiply, because we're just going to multiply each element together. And then we want to sum them all together. And remember, when we're using sum, we need to tell it whether we want to sum the rows, or we want to sum the columns, or if we want to sum all the elements together. And this will define element G, I, J. So we should be done. Okay. So we've tried out 4 different kernels here. We've got a mean smoothing kernel, which is used to denoise images with noise on them. And the Gaussian smoothing kernel, which is used to blur images. And this edge detection kernel detects vertical edges, and this edge detection kernel detects horizontal edges. And then by combining these 2 together, we can get a good picture of all the edges in the image. Now, if everything worked right, we should be able to run our test and see if everything worked, and it did. So what we're going to do in the next set of tutorials is we're going to start to, instead of just using these kernels which we've used to blur images and do classical image processing things. We're going to start to use templates of things that we're looking for. So in the next tutorial, we'll look for a series of circles. And then after that, we'll start looking for Wally.